What's up, guys? I'm going to be doing a lecture today on algorithms. So this is a very introductory lecture. This is meant for somebody who is just starting in their first data structures and algorithms class. So I'm going to be going through a very simple example with a linked list and describing, not focusing on the specific aspects of the algorithm per se as the focal point of the lecture, but more of how to think about a problem, how to think about a specific case in the problem, how to generalize it out to an algorithm, code the algorithm, and then test the algorithm. So this is actually going to be a really, really useful skill for people who've gone basically beyond their first year of programming and now are getting into, yeah, I know how to program, I know object-oriented programming, I know how to write all my functions and stuff, and now you're being given problems where people are going to come to you and say, I want you to write this software, and you're going to have to say to yourself, well, I know how to program, but I need to design. I need to write a design for this thing. So data structures and algorithms are critical for the design phase of software development. So the first example, it doesn't really matter what I chose, but in this case, I chose a linked list and an insert just as kind of an introduction so that I can show you how to take a algorithm and break it down, genericize it, and code it and test it. So I think it'll make sense in a couple of minutes here. So this is just an introductory slide here to show you what a linked list is. I didn't make this PowerPoint presentation just for this video. I made it for my algorithms class, and basically I decided, oh, I made the PowerPoint presentation, I might as well make a video for it. So I don't, because if I just sent this to somebody, it wouldn't make any sense. So this is just describing a linked list data structure. I'm not going to go into super huge detail here because uh, the point of this is not to talk about the rigorous details of a linked list. But a linked list is basically a series of elements where every element or node in the list points at, has a reference to the next one. This would be how we would create, if I wrote this class for a node, in which case really the only property that matters is the next value, or sorry, the next variable, member variable. The value member variable is there just so you can differentiate between, it wouldn't just be a bunch of green boxes. So this is the A, this is the B, this is the C. And you can see what I've done is in the main program, I've said, oh, create a new node for A, create a new node for B, create a new node for C. So I'm doing new. That's where the three nodes come from, and the set next are where the references get set. So, like I said, I'm not going to go into rigorous detail about the linked list, but understand that that's what a linked list is. So we know what a linked list is. It's just a bunch of basically objects that point to the next object, and one of the things that you might want to do in a linked list is insert something in the list in any arbitrary position. So, when you say I want to insert node in a certain position in the array, you have to give some indication of where in the list. So, obviously you're probably going to want to use a number. So these are kind of just like imaginary positions, so that if somebody comes along and does this line of code, insert node n at position 2, it will start basically counting. It'll say, okay, here's the first, it'll follow next, okay, here's the second, it'll follow next, and here's position 2, and that's where we want it to be. So this slide is to show you basically what an insert would look like generically speaking. This is the goal. So that's what a linked list is, and this is how you would alter that linked list in order to insert a new node. So you can see the only things that have changed, if you look at B and C here, in this, it's very obvious. A points to B, B points to C. But after we've done an insert, B no longer points to C. B now points to N, and N points to C. And now that's basically the only two changes we made. So I think so anyway, yeah. So basically we needed to change, we needed to take a new node, get the new node that we wanted to insert, and then change B to point to the new node, and then take the new node and point that at C, which is exactly what we have right here. So that's the setup. Now we get to the real stuff. So algorithms. Somebody comes to you, this is actually an assignment I gave my algorithms class a little bit ago. So hey, good for you if you haven't done your homework yet. This is probably going to help you do it. But uh, if somebody gives you an assignment and they say, I want you to code a linked list and be able to code the insert algorithm, I'm going to go through and show you how to do that, not only for a linked list and not only for the insertion algorithm, but for any algorithm. So the real reason I'm making this video is because for my algorithms class, we're getting into the topic of recursion, and I'm going to be asking my students to break down a much more complicated algorithm, and to be able to do that, they're going to need to analyze the algorithm and take a step back, think about it, and follow these steps in order to actually be able to code and implement it. So while you're watching this, just kind of know that this is not about linked lists. This is not about inserting nodes in linked lists. This is about analyzing algorithms. So what we just saw was inserting a linked list. So the first step in analyzing an algorithm in order to be able to actually code it and use it, I guess I'm kind of skipping over the part that I just did, which would be like, say you were doing you were introduced to a new algorithm you've never seen before. So that's what I just did, basically. You go to Wikipedia and you say, hey, how does quicksort work? And you read it, and then you understand what data structures are involved, what the algorithm kind of is like. So the first step is actually not that hard. It may seem hard and intimidating at first, but it's really not that hard. So the first step is to just define a single example, and this is very easy. So basically, this is a bullet list of instructions that we can follow to accomplish that insert that we just did. So this is what we have, and we want to mathematically and algorithmically define exactly what we need to do in order to get that node, basically in order to reach this end state here. So basically, an algorithm, the definition of an algorithm is an unambiguous, repeatable set of instructions that you can follow so that it will always solve the problem. So how can we say, basically, how can we lay out an unambiguous, reproducible set of instructions that will take us from here to here, no matter what the size of the list, no matter where we want to insert the node. So that's the goal, to go from here to here. And that's what this slide is. Define one example, and that will help you figure out in a specific case what the instructions are going to look like, what the steps of the algorithm are going to look like. So it says here we want to insert node n to be at position 2. So that's the very first thing I did is I said, well, we have 3 nodes, and I'm going to just call them 0, 1, 2. So I'm saying to myself, if somebody comes along and they say, hey, I want to insert node n at position 2, right, I'm going to kind of assume that means they want it right here in between B and C. Okay, so that's the first part. You just think about it, how you want it to work. So the next thing I'm going to say to myself is, since we looked at the goal state right back here, and we're like, oh, well, B is now pointing at N, and then N it points to C. So those are we know that we can say it in English very easily. That's what we wanted to do. We say, oh, just B points to N and N point to C, and we're done. But it has to be super unambiguous because we're programmers. So I've identified that I want to change this pointer here, this B pointer. So what I've done is I've said, well, we need access to node B. And more specifically, we need access to the node at position 1, okay? So we need access to this node because that's the guy that we need to point at N, right? So you would think that the very next thing that we would do is just say, well, just point B at N. But the problem there is if we point B at N immediately as the next step, we lose the reference to C completely. So imagine if I point B at N, so now B is pointing to N, and C is just floating around there. We no longer have a reference to it. It would get garbage collected, destroyed. So we can't do that. We actually have to change the pointer of C first. So, I'm sorry, the pointer of N first. So you see how the 2 changes we made were we pointed B at N, and we pointed N at C. So we actually have to do the second one first, or else we will not be able to get at C. So, long story short, by obtaining access to B, we are able to obtain access to C because we'll have it as the next one, and then we can point N at it. And the final step is, the easy part, what we knew from the beginning. We just set B dot next to N. So that's that last step right here is where we go B point to N, and then we're done. So the second step that you want to take when analyzing an algorithm like this is to identify the general case, because we don't always want to insert a node at position 2. We want to insert the node at position I. So as I go, if you look as I go back and forth between these, look how I'm not really doing anything except I'm changing the wording to be generic instead of referring to like position 2, position 1. So we define the general case. This is the most important part in defining the algorithm. This is basically the algorithm, okay? The general case is the algorithm. So we want to insert a node n to be at position I, right? So we need access, since before we said, if we want to insert the node in between B and C, we really need access to node B, which is at position 1. So the reason it was so important to do this in the single case is because that allows us to visualize and reduce that to the general case. So I can clearly see that we need access to the node at position I minus 1, because in this case 1 is 1 less than 2. So here it says we want to insert node n at position I. Now we need access to the node at position I minus 1. So wherever we want to insert, we need access to the node right in front of it, right? Because we're going to need that for the next 2 steps. So I called it P. That's going to be like the before node. So the reason I called it P is because we're not talking about the specific case anymore. So I don't want to call it B. It could be any one of these. So they could say I want to insert a node at position 0. I want to insert a node at position 1. They can, if the list is 100 nodes in it, they can say I want to insert a node position 57. So in that case, I would be 57, and node P would be the node at position I minus 1, which would be 56. So set node n dot next to point to P dot next. So this is the step of we want this new node here to point to the after node. So what is the after node? So since P is the before node, P dot next is the after node. Well, that makes sense. So n, the new node that we're inserting, will point at the after node. That's what this third line means. And then the very last step is take the before node and point it at the new node. So that's only step 2, believe it or not. So the next, you might think that, oh, good, that's the algorithm, we're done. But, actually, I thought this was going to be a different slide. But so to actually code this, this should be pretty obvious. But you take the general case and you code it, right? So all I'm doing is I'm, by the definition of this new function, insert node at position, right? I'm saying, hey, here's the new node, and here's where I want to insert it. So maybe I have maybe I have a node of 100 elements, and I'm saying, here's a new node, and insert it at position 25. So that's kind of what this first bullet point is saying, that we need this function. Second bullet point is, hey, I need, if they invoke this with 25, then I need to find node 24. So the very first thing that I do is I say, hey, I need the previous node, which is get node at position minus 1, right? Take note of the fact that get node at position doesn't exist yet, but moving on. So we get the before node, the previous node, then we move on to the next 2 steps, which is, like I said, very simple. They're just sets. The code it looks pretty simple. Get the previous node, take the new node, set the next node to the previous node's next node, and then take the previous node and set its next node to the new node, and that's it. That's it. That's the general case. So we've implemented the general case. We've gone from defining the general case to implementing the general case. It's really important. That is like the most important part, is being able to identify understand the data structure, understand the operation, identify a single case, translate that into a general case, and then actually code the general case. So that's the hardest part. We've already got through the hardest part. However, there's still more. But wait, there's more. Step 4, implement subroutines. So you'll notice, again, I pointed out that get node at position doesn't exist. That was like something that I wrote. I was like, well, I'm going to need this function. I'm just going to write it and pretend it exists. Well, now I have to actually implement it. So how do we get node at position I? So, you're going to find yourself in this situation where while you're implementing the algorithm, you find kind of mini algorithms that are part of the bigger algorithm. So now all of a sudden, in order to do an insertion algorithm, I need to do a get node at position I algorithm, which is a smaller piece of the bigger algorithm. So this is this is the way it works. This is what you're going to be finding yourself doing as you write more and more complicated algorithms. Luckily for me, luckily for us, get node at position I is pretty easy to do. When you're working with linked lists, you basically just create a temporary node that's a walker, and then you just move it I times by saying walker equals walker.next. So you can see here, it's a simple for loop that says, if I want to get the fifth, if I want to get if I want to get the fifth node, then I just point the walker at the beginning of the list and then move it to the next one 5 times. So that's all there is to it. So that one was easy. All right, now the last thing. The general case is the general case, but it's not the complete algorithm. There are things called edge cases. Edge cases are special cases that don't apply to the general algorithm. In the case of inserting a node into a linked list, there's 2 edge cases. The first is we want to insert something at position 0. If you follow the instructions for the general algorithm, it will not work. In other cases, if you want to insert an item at the end of the list, and that also, in that case, it won't work. So if we have a list of 100 things, if we try to say I want to insert at position 100, it won't work. If we try to insert at position 0, it'll work. For all the other 99 numbers, it will work. So you have to identify edge cases, and you can do this. You could do this after the fact. You could just write the general case and then test out your code and then just watch it break if you want, or you can kind of identify them at the beginning. I usually, to be honest, I usually just do the edge cases at the end because I just try the general algorithm and I'm like, oh, it doesn't work when I use 0 or something like that. But at some point in time, you're going to have to identify the edge cases. So those are the 2 edge cases for insertion of a linked list node, and I'm going to name these new subroutines append and new root. So if we're putting something at the very beginning of the list, we're basically creating a new root for the list, and if we're putting something at the end of the list, I'm just calling that append. So this is all kind of boring. I didn't want to just say just do it, so I did make a slide showing how to do it. So by implementing append, it's really easy. I would just say, well, okay, I'm appending a node. I want this node to go at the end of the list. So what am I going to do? First, I just say, give me the last node in the list, and then take that node and set its next to this new node. That basically appends a node to the list. That's great. That's done. The only problem is I've used this get list size function that also doesn't exist. So now I need to write that as well. So now I'm writing another function called get list size. Again, this is just a simple walker loop that says, started at 1, walk through the whole list, give me the size. So that's how you would code append using get list size. You can see the logic for append is very simple. You get the last node in the list, and you just set its next to the new node. So that's append. And a new root is even easier. You pass in the new root. You say, new root, I want you to set your next node to this because this isn't the root anymore. Now you're the root. And then we return the new root. So the details of the edge cases don't matter that much in this context. I just want you to understand that sometimes there are situations where back here when we wrote the generic algorithm, that code will not work. So that code that we wrote there will not work in the case of insert at 0 or insert at the last element. So now that we've done that, is this last slide. Step 6 is complete the algorithm. And complete the algorithm just means put the edge cases above the general case, right? So you can see there, I'm saying, okay, here's my full function. Here's the full implemented algorithm. Insert node at position. Here's the node, here's the position. So the very first thing I do is I check for the edge cases. I'm like, hey, are you trying to insert a node at position 0? If you are, then I want you to call this other code that I wrote, new root, and then be done with it, and then go away. And then we're done. Okay, you didn't do that? Well, what about this other edge case? What if you're trying to, just really append something at the end of the list? If that's the case, then call this other function that I wrote. However, if those two edge cases are not true, it will fall through to the general case, and all in in a list of a size 100, all 99 of the other nodes, the general case will work just fine. So that's basically it. So the skill here, the main skill here, I shouldn't go to the next slide yet. The main skill here is to understand the algorithm, define the single case, abstract it out to a general case, code the general case, identify any edge cases and subroutines that you have to code to make it work. So you really, really have to think about it. Sit down with a piece of paper if you have to and draw it all out. You'll notice the seventh step here is compose and test, right? So, like I said before, I kind of my style of breaking these things down is usually to just test it without the edge cases, and that's how I figure out what the edge cases are. So you can see here what I've done is first I just say ABC, right? So then we have what we started with. We have three nodes that are just pointing at each other. And the very first operation I do was what we did at the beginning. So this is actually the same exact code that we started with, except for the last two inserts. So I'm right there. I'm testing that n goes in between B and C. And if you look at what it programmed out at the end, you can see in the middle there it says A, B, and C, right? So the A, B, and C is exactly what we saw back in the first or second slide. So that worked. Insert n at position 2 worked. Now, if I had not coded the edge cases, these next two lines of code would not work. So what I'm doing with insert node I at position 0 and insert node L at position 5, those two lines of code are testing the edge cases. So these three inserts, N, I, L, are testing the general case, the first edge case, and the second edge case. And notice how when I said insert I at position 0, there's the I at the beginning, and when I said insert L at position 5, there's L at the end of the list. And then I printed it out. So that's it. So now that I have my complete algorithm coded, I come in here, I test the general case, I test the edge cases, I play around with it. You can be doing this while you're coding it and testing things out, or you could wait till the end and try it. I think it's better to be testing along the way because you'll find things and maybe stop yourself from going down the wrong path. So I would be kind of playing with this while you're doing the other stuff, but I put it as step 7 because this is kind of the last thing you have to do to know that you're done. So that's pretty much it. I am about to do a video on recursion, and recursion is a big part of a lot of complicated algorithms that you can't really do without understanding the process of thinking about an algorithm, breaking it down, genericizing it, implementing it, identifying the edge cases, identifying the subroutines, and then putting all together and testing it. So I'm going to be doing that, and I hope this helps. I really think that it's important to be able to do this in a generic, abstract way that isn't specific to data structure algorithm, not specific to linked list, not specific to insert in the linked list. I'm going to be asking my algorithms class to basically implement a merge sort, which is a very complicated, well, not very, but it's a fairly complicated multi-recursive algorithm. So, they're not going to be, they wouldn't be able to really just take that and run with it unless they're given this kind of guidance as to how to mentally attack a problem like this. You really need to be able to identify the algorithm and go through this kind of linear process of how do I get from from nothing to the point where I've actually implemented the whole algorithm. So if you follow these steps, I think you should be able to have some more success implementing even really complicated algorithms as long as you take it one step at a time, like I've shown here. All right, me and Sambar will see you later. Goodbye.